All right. Just to continue from yesterday, sorry, what's happening? Okay. Sorry, 2 seconds. I'm still lost. Gone through this. There we go. All right. So the temperature dependence. There's Gibbs free energy, delta H. They're all temperature dependent. So the temperature dependence of equilibrium constant K depends on delta H and the standard enthalpy change of a reaction. So delta H may be calculated from a standard enthalpy of formation for the species delta H Fi, just like delta G. So you've seen this before. I'm sure you've seen it in chemistry. If you've done advanced higher chemistry or A-level chemistry, you should have seen it last year as well. Delta H equals the sum of Vi Hi and Vi delta H Fi. So delta H is the enthalpy of formation. The enthalpies of formation usually listed at 298.15 K, or if you have access to NIST, which everyone does, you can get the list for various different temperatures. If in the exam you'll be given the delta H and the delta H of formation, so you don't have to go through steam tables, and they're all from NIST. The enthalpy change of formation for an element is 0. And all the terms on the right-hand side depend only on the reaction temperature. Delta H also only depends on temperature. So everything on the right-hand side depends on temperature, and delta H depends on temperature. Like delta G, delta H also has units of joule per mole. However, just like delta G, the per mole is per mole of a reaction rather than per mole, to find the heat effect in joules multiplied by epsilon. We went through this yesterday. So the temperature dependence of K is important because it is necessary to find the direction and extent to which the reaction equilibrium will shift with temperature change. So whether it's exothermic, endothermic, if you increase the temperature, where will the equilibrium lie, all based on Le Chatelier's principle. The temperature dependence of K is also important because it is necessary to find a value for K at any temperature where delta G is unknown. To see how K depends on temperature, to find K with respect to temperature, it is necessary to determine the first derivative of K with respect to temperature. So, dK over dt at constant pressure with respect to temperature, and equals d over dt constant pressure e to the power negative delta G over RT. So the derivative of y equals e to the power f of x is given by dy over dx equals e f of x d over dx f of x. You've seen this in maths. Hopefully you didn't do too badly in the previous recent tests. Differentiate the function using this rule gives dk over dt at constant pressure equals e to the power delta G over RT. D over dt at constant pressure negative delta G over RT. Substituting for the equilibrium constant using the definition, dk over dt at constant pressure equals k d over dt at constant pressure minus delta G over RT. And bringing the equilibrium constant to the left-hand side, you get 1 over k dk over dt constant pressure equals d over dt at constant pressure minus delta G over RT. But the left-hand side is also equal to d log of k over dt at constant pressure equals d over dt at constant pressure minus delta G over RT. the derivatives on the right hand side must now be found. Recall that, remember, delta G was defined as delta G equals the sum of VI, GI initial. So GI is per mole and VI is your stoichiometric balance. Turning the derivatives on the right hand side, turning to the derivatives on the right hand side, d over dt at constant pressure minus delta G over RT equals d over dt constant pressure minus the sum of VI, GI, so your delta G over RT. And d over dt at constant pressure minus delta G over RT equals the sum of VI d over dt minus GI over G being the molar G over RT. And the derivative for an individual component is needed, so the infinitesimal change over infinitesimal constant change of T at constant pressure multiplied by G over RT, so eliminating the VI, equals 1 over RT infinitesimal change of G over the infinitesimal change in T at constant pressure minus G over RT squared. And the partial derivatives on the right hand side has already been identified as S. You've seen this before from the previous topic for pure species. So infinitesimal change over infinitesimal change of T at constant pressure, G over RT equals negative S over RT minus G over RT squared, and infinitesimal change over T, and change in T at constant pressure, G over RT equals minus TS plus G over RT squared. Using the definition of Gibbs free energy, where G equals H minus TS, this becomes infinitesimal change over change in T, constant pressure, G over RT equals negative H over RT squared, which in turn becomes GI over RT equals negative HI over RT squared. HI is your enthalpy of formation. This expression is known as the Gibbs-Helmholtz equation. The original temperature dependence of K was d log of K over dt equals negative VI, the summation of VI d over dt GI over RT. So the Gibbs-Helmholtz equation is quite often used to find the specific K values. You calculate these K values, and from the K values, your equilibrium constant, you can determine how your reaction will proceed in which direction, whether it will proceed spontaneously, the various different, or in phase behavior, you can determine how your molecules will behave. Now, this is all you need to know is that's the Gibbs-Helmholtz equation, and this is the revision you use to get there. Next year, you'll find out more about it and also relearn the derivation. So if you substitute the previous equation here, you'll get d log of K over dt equals sum of VI HI over RT squared. By the standard enthalpy change of a reaction, delta H 0 is delta H equals the sum of VI, the stoichiometric balance, times the HI, the molar enthalpy, and d log of K over dt equals delta H 0 over RT squared. To adjust the equilibrium constant from one temperature to another, this must be integrated. So between specific temperatures. This last equation determines the temperature dependence of K, is called the Van 't Hoff equation. So d log of K over dt equals delta H over RT, the Van 't Hoff equation. So you need to recognize these equations, what they are, and as long as you recognize what they are. If you can learn how to drive them, it would be a bonus point for next year. The equilibrium constant depends only on the temperature, as does delta H. So Le Chatelier's principle, or simply Chatelier's principle, can be stated as follows. For a chemical reaction at equilibrium, Whenever the temperature, pressure, or concentration of the reacting mixture is changed, the equilibrium will adjust to oppose the change until a new equilibrium state is established. So that basically means if you have too much of one component on one side of on the reactant side, your reaction will proceed until there are more products. If you have too many products, your reaction will slow down until everything's balanced. Equilibrium equation and its temperature dependence are Xc, so the molar amount of Xc to the power C multiplied by Xd to the power D over Xa over to the power A X B to the power B equals Kp over P0 to the power negative V, and d log of K over dt equals delta H over RT squared. So the effective temperature on the equilibrium constant depends on whether the reaction is exothermic or endothermic. So what a temperature rise or temperature decrease will do is only affected if your reaction is exothermic or endothermic. So if it's endothermic, it requires more energy, it requires more heat. So as the temperature increases, the reaction will proceed faster, so your equilibrium constant changes. If delta H is exothermic, as T increases, K decreases, and reaction must shift to the left to minimize the change. If delta H is endothermic, as temperature increases, K increases and reaction must shift to the right to minimize the change. So shifts to the right, more products, shift to the left, less products. Pressure affects the equilibrium through the second term on the right hand side of the equation below. It's quite obvious, so if you have two pressures, the pressures will determine how your reaction, how your equilibrium constant changes. For A plus B plus C plus D, that's your equilibrium. That's how you calculate your equilibrium constant, and you've done it yesterday. The effect of pressure depends on the sign of the overall stoichiometric coefficient, defined as V equals sigma Bi. Applying this equation to the reaction shown, A plus B plus C plus D leads to an overall stoichiometric coefficient of V equals C plus D minus A plus B. That's quite important. So your products minus your reactants is your overall V. Same if you're calculating delta H, your products minus your reactants. And whether something is exothermic or endothermic determines its sign as well. There will either be an increase, decrease, or no change in the number of moles as the reaction proceeds, depending on the overall coefficient. So your overall coefficient determines where your reaction will lead, whether you'll have more products, less products, or no change whatsoever. There are three cases. If V equals 0, no change in the number of moles across the reaction. In this case, pressure then has no effect on the equilibrium composition, since P over P0 to the power negative V equals 1. So if the number of moles you have on your reactant side and the number of moles, stoichiometric moles you have on your product side are equal, then increasing the pressure or decreasing it doesn't affect your reaction in any way. That's Le Chatelier's principle. If V is bigger than 0, more moles generated by the reaction, increasing pressure lowers P over P to the power 0 to the power negative V and pushes the reaction to the left hand side, so to the product side. And if V is smaller than 0, fewer moles generated by the reaction, increasing pressure raises P over P, P0 to the power negative V, and pushes the reaction to the right hand side. This again is in accordance with the Le Chatelier's principle. To oppose increasing pressure, the reaction must produce fewer moles as the reactant proceeds. If V is smaller than 0, this shifts the reaction to the right, so fewer moles. If V is larger than 0, this shifts the reaction to the left, fewer moles. And if V equals 0, shifting either way produces no change in the number of moles. Equilibrium does not shift. That's an important concept to remember for many years to come. If the temperature and pressure are fixed, then the product on the right hand side of the equation below cannot change in value. So raising the concentration of one reactant component, providing excess, increasing the denominator tends to make left hand side less than the right hand side. So same way pressure affects the Le Chatelier's principle, the concentration also affects the Le Chatelier's principle. So to restore the equilibrium, the reaction must shift to the right hand side and create more products over reactants to balance, to make the system reach equilibrium. The same effect is produced if products are continuously removed, but now the numerator decreases. To restore the equilibrium, the reaction again shifts to the right. So this is how continuous processes are produced rather. So if you're continuously producing something, you remove your product as it's being produced to make sure that your system doesn't reach equilibrium. Because as soon as it reaches equilibrium, you have no reaction anymore. And you want to constantly produce products. Hence, if the concentration of reactant is increased or product decreased, the equilibrium shifts to oppose the change and create more product species. The temperature dependence of equilibrium constant is expressed by this relationship. So d log of k over dt equals delta h to the 0 over RT squared. In order to integrate this equation, first separate the variables and fix the limits. So d log of k within k2 over k1, integrating within k2 over k1, equals delta h over RT squared with respect to dt between t2 and t1. It is known that delta H is independent of pressure and depends only on temperature because it's enthalpy. However, as a first approximation, it may be regarded as constant, so that log of k squared, k2 over k1 equals delta H over R, integrating dt over t squared. So we assume delta H is constant for this purpose. Completing the integration using simplifying assumptions of constant delta H leads to log of k2 over k1 equals negative delta H over R 1 over t2 minus 1 over t1. The results obtained above is reasonably accurate over short temperature intervals. So if you have small temperature differences, you can assume delta H is constant. Where the difference in the heat capacity of products and reactants does not significantly affect delta H. In using the above equation, K1 is needed at some initial temperature T1. This is usually 298.15 K, and the equilibrium constant K2 may then be calculated at any other temperature T2 using approximate relationships. We'll do a question on this. Instead of using algebraic equation, it is also possible to use an experimental chart like the one below. So you can calculate, or rather measure K as temperature changes and create effectively a graph where from the graph you can create a model. From the model you can always calculate your K. Now to a decent degree of accuracy, and that's usually how it's done. Notice that y-axis is log of K while the x-axis is 1 over T. Now a lot of the times when you get K from various different books. You always are given them as log of K, so you should run natural logs of K. So you need to, when you're using K, you need to make sure you have taken the exponential of the K values. Increasing temperature reads from right to left along the x-axis. So if a reaction is exothermic, then increasing temperature leads to decreasing equilibrium constant, the red line, and the reaction shifts to the left. And if it's endothermic, shifts to the right as the temperature increases to the product side. Reading from a chart is generally less accurate than solving an algebraic expression. Well, until you have a digitized chart, but that expression is quite old. So if you have an equation for a chart, or your chart is based on hundreds and hundreds of experimental data like NIST, and you can develop an equation from, you can always solve or interpolate for that specific point using that equation. Let's say it's a polynomial, x squared plus x plus whatever number. That's how equations of state work. They're cubic equations of state, like SRK, x squared plus x plus a specific number, and that's how that equation of state works. So each component is one of your x's, and the final number is usually based on the BIP. The binary interaction parameter is calculated using experimental data. So you take the experimental data, you calculate what it should and what it theoretically is, and then you move your graph and you add a specific number. Next year you'll get to binary interaction parameters. So pi I xi to the power of vi equals k p over p0 or p initial to the power of negative v. And split out the pressure terms from the standard pressure and rearrange as follows, and you'll get xi vi equals kp to the power of negative v 1 over p initial to the power of negative v. That's your power laws. And xi vi p I to the power of the summation of vi, so all the stoichiometric terms equals k 1 over p0 to the power of negative v, and pxi to the power of vi equals k 1 over p0 to the power negative v. Applying Dalton's law to the left hand side will gain you pi vi equals k 1 over p0 to the power negative v. And the products and questions on left hand side involves partial pressure of each species. Kp is defined as follows. Kp equals pi I rather, pi to the power vi. And Kp and K are linked through the expression below. So Kp equals K with respect to pressure to the power of V. And the standard state pressure was formerly 1 atmosphere, but this has been changed to 1 bar now. Depends on what manual and what book you're using. So if you happen to go into the oil industry, because everyone's over 70 years old, it seems, or living in that era, a lot of the times in the UK it's 1 atmosphere, or if it's an American company, then you're working in PSIs, 14.5 PSIs. But this is 1 bar in most European companies. As a result, Kp is numerically equal to K. However, Kp has units of bar to the power of V. Chemists often use Kp formulation since this suits their experimental measurements. Engineers may use the above relation to convert Kp back to dimensionless K. And the reason for that is the difference between gauge pressure and atmospheric pressure. In the student guide notes, to make matters clear, there is a second derivative for Kp if you want to go through it. The equilibrium conversion with respect to reactant species I is widely quoted in literature. The equilibrium conversion is the number of moles of species I, so that specific species that has reacted at equilibrium, divided by the total number of moles of species I initially present. So equilibrium conversion may either be expressed as a fraction of a percentage, or as a percentage rather, fraction or a percentage. Hence, the definition of equilibrium conversion often is denoted by the symbol xi, as given by xi equals vi epsilon over ni 0. So the sum of all stoichiometric terms over the number of the full number, where vi is modulus of the stoichiometric coefficient of reactant species. Although any reactant may be used, the equilibrium conversion xi is usually quoted for the limiting factor, or the limiting reactant. That's pretty much for the lecture part.